So if you remember my previous lectures, those supervised question decomposition methods are very costly. For example, you don't know what is the point that should be split for each sentence and so on. They are very costly. And that's why we are interested in unsupervised question decomposition. And this is a very great paper, Unsupervised Question Decomposition for Question Answering. So, we first create a pseudo-decomposition, and then we learn what we have done, because this part is a little bit offline. Let's use the word offline because we are not using it in real time. So after we created these pseudo decompositions, then we can use it sequence to sequence model to learn them so that we can do it fast. And then it is ready. And so first we say that we have hard questions, and hard questions, it means it is more than one hop. But hard questions are multi-hop. And we have simple questions. There are one hop, like the questions that in web questions in 2013, that data set. It just needs, if you just search it in Google, it gives you the answer. There are simple problems. Let's talk about Hotpot QA. For example, here there are lots of questions for which in comparison to who or what. And so this is a really interesting thing that you see the proportion of them. So two paragraphs contain question relevant. For each question, Hotpot QA provides 10 context paragraphs. Like when you do search in Google, you search something, it gives you a list. But most of the time, the first 2 or 3 are most relevant, and then the more it gets to the end of the list, you see that they are not relevant, they are irrelevant, they are distractor paragraph. The same thing are here. We have in Hotpot QA provides 10 context paragraphs. 2 paragraphs, the first 2 contain question relevant sentences called supporting facts, and the remaining paragraphs are irrelevant. So first, in this approach, we want to create a noisy pseudo decomposition by just using embedding similarity, what we do in very old self-supervised learning, in machine learning. And then we train a decomposition model with unsupervised, because what we have done is good for offline. We want to do it fast, so we create sequence to sequence model to learn it fast. Then we can use it for inference. So we can use this for inference, not this one. And after that, we validate that on multi-hop, where questions require reasoning over multi-hop pieces of evidence. So as I said, we have 2 types of questions, simple or hard. Simple, single hop, you can just Google this and answer the question. But hard questions, if you Google hard questions, then you will see that Google will return very irrelevant results, because semantic web is still at its infancy. I don't think Google is using semantic web and SparkQL for graph databases in order to answer what we are querying in Google. So that's why the hard questions are multi-hop, and they need to split into some simpler questions. So the usual way is you maximize the answer given your context, which is lots of paragraphs, and your question. But the easier objective is that you maximize the likelihood of the answer given your context. and the question, but this time you're conditioning on a set of sub-questions and sub-answers. So you are conditioning more, and this gives you good flexibility. So the easier objective is this, and as I said, it's too expensive for human to do supervised decomposition models. That's why this paper introduces Onus. It's an algorithm. As I said, we map a question into sub-questions via unsupervised techniques. You may seem that this is very slow. Yes, this is slow, but we are just doing it for offline purposes. We are not doing for inference. Then, because we know the answers with the single, we find the answers with the single hop, and then we use these sub-questions to predict A. But before that, we should, of course, do a sequence-to-sequence map in order to make this faster. Because we don't want to just do as enumeration at the inference time, because it's very slow and it's not tractable and feasible. So unsupervised question decomposition, as I said, we have two types of questions, hard questions and simple questions, corpus. So our corpus is, we can separate it into two parts. So this is the first things that comes to the mind. First you say, okay, this is my positive things. I want to increase the distance. So I want my question, what are the decompositions, SI? And we want them to be very diverse. I want them to be very different, these sub-questions to be very different with each other, which is a very clever idea. And then after that, after these pseudo-decompositions, we should learn them, because we should do it at the inference time, so we should learn them as a sequence-to-sequence model to avoid those enumerations and those things that we are allowed to do it offline only. And in one-to-one unsupervised sequence training, we use unsupervised learning to map one question to n sub-questions. So we start with paired question and decomposition, but do not learn from the pairing because it's noisy. Instead, we use unsupervised sequence-to-sequence model to learn this question. You can do it any recurrent neural network, or even you can use transformers. Anything that relates sequence to sequence would be fine. So the creating pseudo decompositions, you see, instead of this, in practice, first of all, that measure f could be a simple dot product like this. And second of all, we don't do this like this. We don't enumerate everything. We just use top K of this to make it fast. So if you do this, just the top K of this term, then that's a good start. That's at least a good warm start. And the random retrieval, for comparison, we test the random pseudo decomposition baseline, where we retrieve these sub-questions by sampling uniformly from S. And then we edit it because sub-questions are retrieved base, so they are not often about the same entities as Q. So inspired by this method, I will give you at the end of this lecture, we replace each sub-question with an entity from the same type. For example, if it is location, date, and this step is important, but not onus. So, as I said, we need something like language model because we don't know, they are retrieval based. We should substitute these words with some words that are more appropriate in the context And what is better than these transformers? Transformers are good for if your sentence is very small. I mean, we don't care about the computational complexity of that. Although transformer has a big computational complexity in comparison to attention-based LSTM, but it is good for mask language model of reasonably or medium-sized sentences. This is my opinion, of course. And a quick fox jumps over. You see, there are some masks, and we can easily predict it. And it is self-supervised, so we don't have a problem of labeling, and everything is cheap. And now we are done. Now we do this mask language model, fine-tuning for one epoch in question and pseudo-decomposition via random retrieval using the final weights. And now, of course, this is a very interesting paper. We skip it, and we skip this. So we produce a noisy input D prime by randomly masking, dropping, and locally shuffling tokens. And we train a model with parameter theta to maximize this log likelihood. What is the probability of your D given your decomposition, given your noisy decomposition? And this is the last thing that you need to know. Because now we have the decomposition, so just answer it. Just answer those sub-questions and then recompose them to give the final answer. So for this question, what profession do this and that Albert Camus have in common? We would say that it is a single hop. Who was Albert Camus? This is a simple question. We can say that. What profession? This is another sub-question. So we have only two sub-questions. What profession does Mencken have? The other, who was Albert Camus? So this is SQ2 and this is SQ1. So we have decomposed it in two, and so we answered them separately. This is one sub-question, we answered them. And then because we have the answers, we recompose. We combine those to get the answer, which is a journalist, for example. Journalist. So the profession is the journalist. So both of Mencken and Albert Camus are journalists. And this is a good article. Another good article. And that's it.